everyone, welcome to the second part of chapter 8. So this will be on writing chemical equations, so not just balancing them like we were doing in part 1, but figuring out how to actually write a chemical equation, and we'll also talk about the different types of chemical equations. So different types of chemical equations. There are 5 types of reactions. So these are combination, decomposition, single replacement, double replacement, and combustion. Sometimes, just so you know, you may see combination written as synthesis. Either way is fine. I don't care which one you call them. And sometimes you may see single displacement and double displacement, single replacement, double replacement written as displacement. Again, this is the same thing. This is just an old nomenclature versus a new nomenclature. So there are 5 types of reactions. So we're going to go through and talk about how you'll know the different types of reactions. So a combination reaction is when 2 or more elements form a product, or 2 or more compounds form one product. But essentially, it's 2 things make one thing. So like in this picture here, right? 2 things make one thing. So in the first example with the magnesium and the oxygen, magnesium and oxygen is making magnesium oxide. And in the next one, nitrogen and hydrogen is making nitrogen trihydride. But again, we're going from 2 things to one thing. 2 things to one thing. So that is how you will recognize a combination reaction. 2 things make one thing. Decomposition is exactly the opposite. You have one thing that's breaking into 2 things, or maybe into 3 things, but it's breaking apart. So decomposition reaction, one reactant splits into 2 or more simple substances. So we start with one thing and we make 2 things, just like it shows in this picture. So here, one thing, mercuric oxide, makes 2 things, mercury and oxygen gas. This one, potassium chlorate, makes potassium chloride and oxygen gas. So it's something is breaking apart. So that will be how you'll recognize decomposition. So again, these are opposites. Combination, 2 things will combine together and make one thing. Decomposition is one thing breaks apart into 2 or more things. Single replacement and double replacement are the ones that people get mixed up. So try and keep these separate for you. So single replacement, we have an element reacts with a compound. So an element reacts with a compound. That is how you're going to recognize it. Double replacement is 2 compounds reacting together. So here we have an element reacting with a compound, and what happens is that this element will go and kick one of them out. So they just kind of switch places. So now, instead of A being by itself and B being bonded to C, A is bonded to C now, and B ends up by itself. So A kind of kicked B out, so it ends up by itself. So like here in this first example, zinc and hydrochloric acid, zinc will go and replace the hydrogen. So now zinc ends up bonded to chlorine, and hydrogen ends up by itself. And like in the second example, iron will go and replace the copper. So now iron is bonded to the sulfate, and copper ends up by itself. So single replacement is an element reacting with a compound. Double replacement is when you have 2 compounds. So there are no single elements. We have 2 compounds reacting together, and the elements in them change places. So here, if you'll look, B and D switch. So now, instead of A being bonded to B, A ends up bonded to D, and C ends up bonded to B. So things are switching, right? So like in this first example, we have silver nitrate and sodium chloride. Essentially what happens is the nitrate switches with the chlorine. Okay, you can think of the nitrate kind of acting together because it's a polyatomic. So now silver ends up bonded to the chlorine, and sodium ends up bonded to the nitrate. In the second example, the hydroxide will switch with the chlorine. So now sodium ends up with the chlorine, and the hydrogen ends up with the hydroxide, and this will actually be water. This is another way of writing water. But the ones, like I said, to keep straight, single replacement is an element in a compound. Double replacement is two compounds. Those ones are the ones that people get mixed up. So pay particular attention to that. Combustion reactions, I pointed out last time, and I said that we would talk more about them in this lecture. A combustion reaction is a really special type of reaction. And it always is going to have a hydrocarbon, so something in the front. So this is like I said, a hydrocarbon. And hydrocarbons always have carbon and hydrogen, and they will sometimes have oxygen too. Okay, so it's not just carbon and hydrogen. Sometimes they'll have oxygen. But a hydrocarbon reacts with oxygen gas to produce carbon dioxide and water, and it releases energy, but we're not gonna really worry about that. This is when something burns. This is burning. Okay, so whenever you burn something, right, we burn a hydrocarbon, it's going to react with oxygen gas and always will produce carbon dioxide and water. This hydrocarbon is the only thing that changes. Otherwise, everything else stays exactly the same. So it's still going to react with O2, and then it's going to produce CO2 and water every single time. Just this first thing may be different. And then when that's different, that will also change the balancing. Okay, but the compounds there don't change other than this hydrocarbon. It's always going to be a hydrocarbon, reacts with O2 to produce carbon dioxide and water every single time. That's a combustion reaction. You have to have these three things to be a combustion reaction. If it only has two, then it's not. It has to, something reacts with oxygen gas to produce carbon dioxide and water every single time. So like this is a combustion reaction because oxygen gas, right? We have a hydrocarbon reacts with oxygen gas to produce carbon dioxide and water. So see, this changed, but it still reacted with O2 to produce carbon dioxide and water. So those three things must be the same or it's not a combustion reaction. Again, don't worry about the energy. But if you'll notice, right, from the last one, since the hydrocarbon changed, right, this is the thing that changes, the balancing also changes. So pay particular attention to that. But again, always reacts with O2 to produce carbon dioxide and water. So here's a summary of your reaction types. So we've got combination, decomposition, single replacement, double replacement, and combustion. So this is also shown in your lecture worksheet. You have kind of a summary. You've got like all the blocks in there. And you also have this like summary page to show examples of each one of the reactions. Okay. Again, this here, this looks a little bit weird. This is just telling you that this is a hydrocarbon. That's just how they've chosen to write it. All right, so go ahead and pause here and complete lecture worksheet problem number 3. I also want you to go through, part of number 6. So on number 6, we skipped the reaction types last time. So go through and you should have balanced them already. We should have balanced them after the last lecture worksheet or the last set of lectures. But I told you guys to leave the reaction types alone because we hadn't covered them yet. So go through now and do number 6 as well and fill in the reaction types. Check your work against the lecture worksheet key. And obviously, if you have any questions, send me a message about that. But pause here. All right, now we are going to do the hardest part of chapter 8, and that is actually going through and writing equations. So this is tricky, and we're not going to spend a ton of time on it. This is like an introduction to it because they will have you do more of this in chapter 20. So I want to get some experience with it. So we're gonna learn how to do this. So it says the reaction of methane, which is CH4, and oxygen gas produces carbon dioxide and water. This, right, this is a hydrocarbon. And it says that it's reacting with O2 to produce carbon dioxide and water. This is a combustion reaction. Okay, this is how they'll show up. But it says, write an equation using the correct formulas for the reactants and the products. So it says the reaction of methane gas. So we have CH4. And we talked about states of matter last time. We're going to start including them here if you know them. So CH4 is a gas, reacts with oxygen gas, it tells us is O2, to produce the gases, carbon dioxide and water. So it's telling us both of those are gases. Okay, so that would be how we write this. So anytime you see the word and, that's typically going to signal, plus. So that's why we got CH4 and plus O2 produces will signal you to write the arrow. That's telling you it's going to start talking about the products. And then the gas is carbon dioxide, and again, and will be that plus sign, and then water. So that's how I'm getting all of that. Now, after you go through and actually write them all out, you're going to balance it, right? It says count the atoms of each element in the reactants and the products. So over on the reactant side, we have carbon, we have hydrogen, and we have oxygen. And on the product side, we have carbon, we have hydrogen, and we have oxygen. So again, I always write them in the same order just so that I can keep them all straight. You can write them in whatever order you like. Just, make sure you don't mess it up. So we have 1 carbon here, 4, and then 2, and then 1 and 2. And again, we have 2 in carbon dioxide and 1 in oxygen, or in water, so we have 3 total. So right now, this is not balanced. Okay, so we would need to go through, figure out how to balance this. So our carbons look fine. And I told you guys in combustion reactions, always do carbons and then hydrogens and then oxygens. It just makes your life a ton easier. So then we look at our hydrogens. We have 4 versus 2. So we're going to put a number out front of water to multiply by that 2 to get 4 on the other side. So we'll put a 2 there. When we put a 2 there, that changes our number of hydrogens so that we have 4. And it also changes our number of oxygens, right? Because that 2 gets multiplied there. So we have the 2 in carbon dioxide plus the 2 now in water, which is giving us 4 total on this side. And then we can go through and balance our oxygens by putting something here on the left that'll multiply by that 2 to get us 4. So 2 times 2 gets us 4. So now we're balanced. So that would be the whole process. Oh, I've done this on the previous slide. So we had our 2 there and our 2 there. But whenever it tells you to write a chemical reaction, always go through and balance it. Okay, you're expected, even if I don't say balance it, you're always going to be expected to write a balanced equation because, like we talked about before, you can't have unbalanced equation because they disobey the law of conservation of matter. So you always, always, always must balance your equations. Here's another example of writing chemical reactions. Okay, so nitrogen gas reacts with hydrogen gas to produce liquid ammonia. And you'll see I have this note here that there are some elements called diatomic molecules. And the prefix di means 2. So these are 2 atom molecules. These will be elements that float around in nature as what's called diatomics, as 2 of them. So like we saw some in this last example. O2, that is a diatomic element. Whenever oxygen is by itself, it will always have a 2 at the end of it. It is a diatomic element. And that's true for all of these. So this is Hofbrinkel. So this stands for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So this will be how you remember it, Hofbrinkel. I know it sounds a little silly. You could also say Brinkelhof if you wanted to. But this will be how you remember the diatomic elements. So anytime you see one of these elements, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine, if they are by themselves, they are going to get a 2 after it. So this would be like H2 or O2, F2, Br2, I2, N2, or Cl2. But again, only when they are by themselves. If they are bonded to something, then just follow the normal bonding rules that we've learned before. But if they are floating around by themselves, like where it says nitrogen gas, right? So nitrogen gas, there is nothing else with that nitrogen. It is nitrogen by itself. And nitrogen shows up in Hofbrinkel here. So since nitrogen shows up in Hofbrinkel, it is going to get a 2 after it whenever it stands alone. So if an element is not in Hofbrinkel, it can sit by itself, like we could just write N. But since nitrogen shows up as one of these 7 diatomic elements, it will be N2. So you need to know these. Okay, so it says nitrogen gas, so we'll put a G, reacts with, right? So that reacts with tells us plus hydrogen gas. So hydrogen gas, we look and we try and see, is it a diatomic? All right, because it's hydrogen by itself. It's not bonded to anything. So we look, hydrogen here, hydrogen is in Hofbrinkel, so it is a diatomic. It needs a 2 after it whenever it's by itself. So hydrogen gas, and then it says to produce, that's going to tell us to write an arrow. And then it says liquid ammonia. So we've got NH3. Ammonia is the common name from nitrogen trihydride, and it said it is a liquid. So we'll put an L there. Okay, so now looking at this, we have nitrogen and hydrogen on both sides. And we need to go through and see, is it balanced? And if not, let's balance it. So on the left side, we have 2 nitrogens and we have 2 hydrogens. On the right side, we have 1 nitrogen and 3 hydrogens. So not even a little bit balanced. So let's go through and balance our nitrogens first. So on the left-hand side, we have 2 nitrogens. On the right-hand side, we only have 1. So we're going to put a 2 out front here. When I do that, that 2 distributes to the nitrogen. So now there are 2 nitrogens. And it also, though, distributes to the hydrogen. So we get 2 times 3, which gets us 6 hydrogens. So now, balancing our hydrogens, we need to put a number out front here to multiply by that 2 to get a 6. So that will be a 3. So we go 3 times 2 gets us 6. So now we have 2 nitrogens on each side, 6 hydrogens on each side. So we are balanced. Here's our last example. This says aqueous sodium phosphate reacts with aqueous magnesium chloride to produce aqueous sodium chloride and solid magnesium phosphate. What a mess. So let's go ahead and check this out. So the first one, aqueous sodium phosphate. Sodium phosphate you will recognize as an ionic compound, right? Since this is an ionic compound, we need to write out our ions and circle and switch to get our formula. So sodium is Na+, phosphate is PO4, 3-. So the 3 goes to the sodium. The imaginary 1, right, will go to the phosphate. So this will be Na3 from that phosphate. And then we don't need to put parentheses around the phosphate because the 1, right, the imaginary 1 for the sodium would go out here. But we don't write 1s, so we don't need to write phosphate in parentheses because there would be nothing on the outside of it. So sodium phosphate, that's our first one. Na3PO4, and it says it is aqueous, so that is the AQ. Reacts with, so that would be a plus, aqueous magnesium chloride. So magnesium chloride, again, is an ionic compound, so we need to write out that formula. So up here, so magnesium is Mg2+, chloride is Cl-, so when we circle and switch, that 2 will go out to the chlorine. So this will be MgCl2. So reacts with aqueous magnesium chloride. And then to produce, that's telling us to write an arrow. Aqueous sodium chloride. So sodium chloride will be Na+, Cl-, right? That is an ionic compound. Since they're both +1, -1, right, they cancel out, so we can just write NaCl, and that's aqueous. Sorry, I'm starting to write smaller. I realized I was writing out of room. Plus solid magnesium phosphate. So magnesium is Mg2 plus, PO4 3 minus. So the 2 is going to go to the phosphate, and the 3 is going to go to the magnesium. So when we write this, and I'm going to write this up there a little bit. When we write this, we're going to write Mg3 PO4 2. Okay, so that's magnesium phosphate. So now looking at this, we need to figure out, oh, and sorry, this is a solid. We need to figure out, is this balanced? And if not, we need to go through and balance it. This is one of the trickier problems that you would come across. This is about as hard as I can make it, where you have to write out the ionic formulas and then circle and switch. So let's go through and balance it. So on this side, we have sodium, and then we have phosphate, and I'm going to keep the phosphate together because if you look on this left side, it stays as PO4, and on the right side, it stays as PO4. So since the phosphate doesn't change, right, the number of phosphates changes, but the phosphate itself doesn't change. So since the phosphate doesn't change, I'm going to leave it as PO4 and count how many PO4s on each side there are. You can break it into phosphorus and oxygen if you want, totally fine. And then we also have magnesium, and we have chlorine. So now on the other side, we're going to look sodium, phosphate, magnesium, and chlorine. So on the left, we have 3 sodiums, we have 1 phosphate, 1 magnesium, and 2 chlorines. On the right, we have 1 sodium, we have 1 chlorine, we have 3 magnesiums, and we have 2 phosphates. So now we need to go through and balance this. I'm going to go ahead and balance my my phosphates first, just because I know how this plays out. But I'm going to balance my phosphates first. I have 1 on the left and 2 on the right. So I'm going to go ahead and put a 2 out front here. When I put a 2 there, that tells me I have 2 phosphates, right? But it also changes my number of sodiums that I have. I have 2 times 3 sodiums now, so now I have 6. So I balance my phosphates. We can go through, we can balance our magnesiums if we'd like. We have 3 magnesiums on the right, but only 1 on the left. So we're going to need to put a 3 out front of magnesium chloride. When I put a 3 there, that gives us 3 magnesium chlorides, or sorry, 3 magnesiums, but now we have 3 times 2, that gives us 6 chlorines. Now I can go through and balance my sodiums, which will also end up balancing my chlorines, but I have 6 sodiums on the left and only 1 on the right, so I'm going to put this 6 out front here. When I put that 6 there, that 6 distributes in and gets multiplied, right? So now I have 6 sodiums, but it also gets multiplied to the chlorine as well. So I have 6 chlorines. So now looking through this, 6 sodiums on each side, 2 phosphates, 3 magnesiums, and 6 chlorines. So like I said, this is about as hard as I can make these problems, where you have to make ionic compounds and write them out and balance it. This is the toughest problem that you could possibly find. What I'd like you to do now is pause and work on chapter 8, but this is, on lecture problem number 8, but this is the end of chapter 8.